In today's video, we're going to be talking about Momentum Homework 2. Now, whether you've gotten to this or not, it's not a big deal. We did enough work with momentum in the classroom that I feel like everyone could be successful with a little bit of practice. Let me show you how I would do these, and then you compare them how you would do these. You can find these, I'll put them in Schoology, a Schoology assignment, so if you don't have this, you can download the Homework 2 and either follow along or complete it on your own. It's up to you. So the first one says, in a freight yard, a train is being put together from freight cars. An empty freight car consisting of coasting at 10 meters per second strikes a loaded car that is stationary and the cars coupled together. One of the things that I like to do here is I like to draw a picture of the actual scenario to kind of help me get my brain wrapped around what's going on. So we have an empty freight car here. And it's coasting in at 10 meters per second. It's going to hit and couple with a full car that was stationary to begin with. So here's the before situation. We'll say this is the full one. Here's the full one. It's at rest. This one's coasting in. This is the before situation. The after side, it looks like this. So we have the one that was moving. It is now coupled, hit and coupled to the one that was stationary. And if it hits, it's probably going to be moving a little bit slower. So here's the before side, and here's the after side. So we're going to need to do two things here. We're going to need to draw the energy bar charts and then the momentum bar charts. So it's not a problem to be able to draw these things. If we put some numbers on here, I think it'll help us to begin with. It says that this one is 3,000 kilograms. This one is 15,000 kilograms. It says it's full of 12,000 kilograms of soda. But it's a car, so it has a 3,000 on its own, so there's the totals there. And so now the total for this one would be 18,000 kilograms. This one's moving at 10 meters per second. This one's at 0 meters per second. And the question is, how fast is this one moving afterward? So that's the basic setup of the question. So let's see what the bar charts look like. So if I go to do the energy bar charts, I have the before side and the after side. This is gravitational, kinetic, and elastic. This is gravitational, kinetic, and elastic. And in here we have, we'll call them cart number 1 and cart number 2. So this is the train car. So train car 1, train car 2. I don't think there's anything else in our system. So what's the energy situation look like beforehand? Well, clearly we see that this car here has some kinetic energy, and who knows how much it has, but we'll give it the standard 4-block treatment. This car here doesn't have any at all. Afterward, they are now moving together. So we'll just make them all blue. All right, and we know that during a collision, if it crashes, there's going to be less energy there. Now, I just put 2 bars there. We're actually going to solve for how much is going on here. We'll be able to see what the actual values of the kinetic energy are coming up. We'll do that in a second, but let's do the momentum. So we have some energy clearly leaving the system. We're going to represent it as 2 right now. We're going to go back and look in a moment to see how much it is. But if we do the momentum bar charts down here, what we have is we have the 2 axes. This up and down axis represents the mass, and this left and right axis represents the velocity. This is the before side, and this is the after side. So let's see what's going on here. What's the situation? Well, we have a 3,000 kilogram car, so we'll give its mass 3,000, and it's moving at 10 meters per second. We could actually calculate this if we wanted to. We see that the vertical is 3,000 and the horizontal is 10, so the total area here would be 30,000. The area represents the motion quantity, which we call the momentum. Now, what about the other car here? Well, this other car here, we'll make it red just for fun. This red car here, we know, you see its mass is 5 times bigger, so I'm going to make the mass 1, 2, 3, 4, 5 times bigger, but it's not moving at all, so it doesn't have any of this motion quantity, it doesn't have any momentum. So what has to happen over here? Well, now if we look at the total mass is now 18, which is the combined mass, and so it's the first one, and then 1, 2, 3, 4, 5. But it's so much taller, which means that it's moving so much slower because the total area here has to match the total area here. But now the up and down is 18,000. And so the question is, what is this velocity? Well, that's cool because I know that the area here is 30,000, so what does this area have to be? 30,000. And since this is the area, you take the area divided by the length and you get the width. So we know that 30,000 has to be equal to 18,000 times the combined velocity. 30 divided by 18 seems like it's, I don't know, 5 over 3, maybe 1.67 meters per second. So if we have this, we've answered the question, can we now figure out what's going on with the kinetic energies? Well, we can in terms of calculating the kinetic energies before and the kinetic energies after. So let's talk about the kinetic energy beforehand. If I look over here, the kinetic energy is just the kinetic energy of this green car here. So the kinetic energy is equal to 1/2 mv squared. The mass is 3,000. And the speed is 10 squared. So 1/2 of 3,000 times 100. So the total kinetic energy is 150,000 joules. Now, what about the after situation? If I look at the after situation over here, it's these guys that are moving together. So what's their kinetic energy? Again, 1/2 mv squared. What's their total mass is 18,000. And their velocity, as we decided down here, was 1.67 squared. So let me take a moment and calculate that. So here the kinetic energy is 25,100 joules. So to me, when I look at this is 150,000 joules to start. Now I only have 25,000. So this is actually 6 times this. So if we go back, we can actually go back and adjust our chart, which would be really interesting. So instead of 4, I'm going to put 5, 6 blocks here. I'm going to put 6 blocks there. Each block 25,000, and then what do I end up with here? Just 1 block of 25,000, which means how much did we lose? Instead of losing 2 blocks, it looks like we've lost a total of 5 blocks. 1, 2, 3, 4, 5. So this is a full situation here that goes with this number 1 in the momentum homework. Number 2. You may be asking what happened to momentum homework 1. We're doing them in reverse order this year. So let's reset and let's see if we can't do number 2. Let me get my little eraser out. Okay, let me fast forward. Let me scroll down on the page. All right. This one says number 2. Let's do number 2. It says an astronaut with a mass of 80 kilograms carries an empty oxygen tank mass 40 kilograms. He throws the tank away from himself at the speed of 2 meters per second. At what speed does he start to move off into space? So this is interesting. So the before picture, we're gonna need an astronaut here. So my astronaut, we're going to draw him thusly. So my astronaut, all he needs is just a space helmet. That's all he needs. He's carrying an oxygen canister. And this is the before situation. So if he pushes it away from him, well, Newton's third law of force pair says that he pushes the can to the right, the can pushes him back with the same amount of force. So what does the after picture look like? So he's here, but he's moving back this way. Little motion lines. And what's happening to the can? Well, the canister's over here, and it's moving this way. Now, in my head, he is 80 kilograms and the canister's only 40 kilograms, so less mass, it should be going faster. So let's put some stuff on here. We know that this is a 40 kilogram canister. And we want to know, oh, he throws this at 2 meters per second this direction. Our guy is 80 kilograms, and we want to know what is his speed in meters per second. Now, you can be using your brain a little bit and have a good sense of, oh, well, if he is twice the mass, maybe he's half the speed. That's a great way to consider this. Let's do the bar charts and see if it makes some sense to us. Do the energy bar charts first. So we have gravitational, kinetic, and elastic. We have gravitational, kinetic, and elastic. So we have the astronaut and the can. Those are in our system. Now, I'm looking over here at my before situation, and there's no gravitational energy, there's no kinetic energy, there's no elastic energy. That to me is weird because I look over here, and what do I notice? Does our astronaut have some kinetic energy? Sure. I don't know how much. So we're just going to put 2 bars for the astronaut, and then we're going to put 2 bars for the canister. I don't actually think they're the same, but we're going to put that for now. The problem is I have these 4 bars of kinetic energy, and I don't know where they came from. And so there's an idea that, well, maybe they came from the astronaut. He is inside the system, but I don't have a good way to represent that. So this is a weird thing. I think the best way to represent this is to take the astronaut out of the system. And if we take the astronaut out of the system, we would have to take off his kinetic energy over here too, because we have to represent that. But maybe the astronaut is donating some energy in, and then they're getting some energy out. So this is a weird way to go. So let's hold off on this. We'll come back to here in a moment, and let's do the momentum. and we'll come back and make some decisions about. All right. So as we know, this is the mass, this is the velocity. So what do I have going on here? I'm going to do these in red. It'll be easier that way. Since I decided to make the astronaut black. Bad decision making. So what do I have going on here? Well, the astronaut has a mass of 80 kilograms, so I'm going to represent this as 80. But he's not moving. But the canister has a mass of 40, so that would be about half that size. So I'm okay with that. Over here, we have the same masses. Here's my 40. And here's my 80. And what do we know? This one's moving to the right at 2 meters per second. And what's this guy doing? He's moving to the left. So I think that we have to consider here is nobody is moving here. So the total momentum, this total motion quantity over here is equal to 0. But if this is equal to 0, what does that mean for this over here? It must also be equal to 0. Remember, this side and this side, the momentum is always the same. And so if it's half the height, or it should be twice the height, it should be so it's possible that these two have the same momentum. Here's the difference. This one is 2 meters per second at 40 kilograms for a total of 80. But this is to the right, so it's positive 80. What does that mean for this guy here? He's 80 kilograms, which means, since these are equal, how fast does this have to be moving? How about 1 meter per second? But it's moving left, and so negative 80 and positive 80 and negative 80 give you 0. So when I go to look at these, we're going to calculate each of the kinetic energies and see what happens here. So the kinetic energy, we'll do it up here. The kinetic energy for the astronaut, 1/2 mv squared, 1/2 of 80 times 1 squared. It's negative 1, but it's 1. So the kinetic energy of the astronaut is 40 joules. Well, what about the canister? (1/2 mv squared), plug and chug, 1/2 the mass, which is 40, but the speed is 2 squared. 2 squared is 4. 4 times 40 is 160. Half of that. So this is 80 joules. So I'm going to adjust my picture here, because what it's looking like is you have 140 and 240s here for 80, and so it looks like there's a 2 to 1 energy ratio where each of these blocks is 40. So 40 for the astronaut and 80 here. So where did the energy come from? Well, I'm representing the astronaut on here, so I kind of have to put him in here. Right? And it's hard to say where he came from, but all the energy had to come from somewhere, true? And so we're going to say that it came from the astronauts. We can do it this way. We can say, oh, he donated 3, even though he's already in the system. Or we could put him on here and do it, but I think the thing that's important is that we realize that in the end we have all this kinetic energy. It had to come from somewhere, and the momentums have to be equal. All right, let's do one more. This is a weird one for sure. It says a 2 kilogram melon is balanced on a bald man's head. His son shoots a 0.5 kilogram arrow at it with a speed of 30 meters per second. The arrow passes through the melon and emerges with a speed of 18 meters per second. Find the speed of the melon as it flies off the man's head. So this is a weird one. So what we're going to have here is we're going to have basically the before situation. So we need a man and we need a melon. So here's the man. In my head, melons are green. So here's the before situation. And what do we have? We have an arrow on its way in. So here's the before situation. What is the after situation? Well, the after situation, it's exactly the same, only different. Okay. So here's the man again. He didn't get shot, but the arrow has emerged on the far side, but it is slowed down because as it went through the melon, it transferred some of its momentum to the melon. But since the melon was stopped before, it's now moving. So here's the before, here's the after. Let's draw the bar charts and see what it looks like. So we have our gravitational, our kinetic, and our elastic. Gravitational, kinetic, and elastic. What's in the system? I think it's probably the arrow and the melon. Okay, that seems good to me. So beforehand, where's all our energy? It's all in the arrow. So the arrow has a bunch of kinetic energy. So we'll go with our standard 4 bars to start. Afterward, the arrow has slowed down, so let's say it lost half of its momentum. I don't know how much, or half its energy. Again, I don't know how much it's lost. We're going to have to go back and revise after. But now, I'm saying if you start with 4, you end with 4. I actually don't know if that's true. I don't know if any has left the system. I'm going to have to calculate the energies after to see, but in order to calculate the energies, I have to understand the momentums first. So let's do the momentums, and we'll go back and we'll revise our energy charts. Okay, again, this is the mass, that's the velocity. So let's label our picture so we know what we're talking about. It's a 2 kilogram melon. And the arrow is 0.5 kilogram arrow. And it's moving at 30 meters per second. So let's diagram this up. The melon is 2 kilograms, so when I draw that, basically we'll say that's 2 kilograms, and then the arrow is a half kilogram, that's a quarter of that. And the arrow is moving to the right at 30 meters per second. So it's a 0.5 kilogram moving at 30 meters per second, so the area here is 15. This one's not moving, no area. The total momentum, the total motion quantity is 15. So what's going on over here? I have the same mass. And I probably know what's happening here. The melon, it passes through, and now the melon is only moving at 18 meters per second. So it's slowed down, not all the way to halfway, but a little bit more than halfway. So let's say it's slowed down to here. 0.5 kilograms, and now moving at 18 meters per second. So now we have 9. So the motion quantity was 15, now the motion quantity is 9. It lost a bunch, but what do we know? The total has to be the same. Was 15, now it's 9, it looks like we're missing 6. So the total area has to be the same. This guy here, we know his height is 2 kilograms, so I wonder how fast he has to be moving. Well, the total area here is 15. I have 9. What else do I have to have here? It must be 6. If the area is 6 and the height is 2, what does the width have to be? 3 meters per second, which means that in the after picture, this is moving at 18 meters per second, and the melon is moving at 3 meters per second. Which is cool, because it allows us to it helps us really understand how the motion works, how the momentum is the same before and after, and now we can go back and we can calculate the energies of our arrow before, our arrow after, and our melon after, and see if we lost or what the ratios are. So let's do the kinetic energy before. So the kinetic energy is 1/2, the mass is 0.5, and the speed was 30 squared. So 30 squared is 900, half of 900 is 450, half of that is 225 joules. All right, so this is 225 joules. We're going to represent it like that. We may put another block on or something, but let's do the afters over here. So the kinetic energy of the arrow after, again, the mass is 0.5, and this time the speed is 18 squared. Give me a second to calculate that. So this is 81 joules. But let's do the melon. So for the melon, 1/2, the mass of the melon is 2, and its speed is 3 squared. 3 squared is 9, half of 2 is 1, so this is 9 joules. So the total energy here is only 90. The total energy here was 225. And so we have a large loss. I don't think there's a great ratio there. So we're just going to, instead of being specific with our representation, we're going to represent it a couple different ways. So let's come over here. And one of the things we're going to notice here is that you can see there's 9 times as many. So there's 9 times as many of this as this, which is crazy to me. And so if we were to represent this, I would say, oh, well, there's, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1. I don't know why they're getting skinnier. So this represents the energy on this side. The problem is that over here, this total energy is only 90. So if I want to do this one, it would have to be 225. So it would have to be some huge, right? This is 90. This would have to be over twice as big. Almost 3 times as tall. So this total energy here is 225, and then what happened as it passed through? Did it lose a ton of energy? Yeah, I mean, basically, as it passed through, it went from 225 down to only 90, and so it lost a ton of energy here. But the idea that we can use the momentum to inform our understanding of the energy really helps out in these complex problems. All right, that is enough for now. If there is a need to do The last couple problems, I'm happy to do them for you. Maybe I'll do them tomorrow just for fun. But that's good enough for tonight.